Hello, everyone. Today I'm going to present our talk, Making Serverless Pay-for-User Relative with Leopard. And I'm Tingjia, and this is a joint work with my advisors, Andrea, Remzi, and Taylor. Service computing, also known as function as service, becomes very popular these days. A recent study shows that AWS Lambda is using around 65% of the cloud architectures. It's popular because it abstracts away the management, letting developers just write the functions. It also offers fine-grained pay-as-you-go billing. Service providers all advertise a pay-for-use model, but what does this pay-for-use actually mean? Suppose a function runs twice, once with a small input, once with a large one. This graph shows the usage over time, the memory usage over time. Under true pay-for-use, users should build based on the actual usage, the area under each curve. But in reality, platforms didn't build based on the actual usage. Instead, users set a memory limit, like tuning a knob, and are charged based on the execution time multiplied by this user-tuned limit. And this graph shows the build area when the limit matches the peak usage exactly perfectly. Additionally, the memory limit isn't tuned per invocation. It's shared across all invocations of the same function. So if you are set this limit high enough to handle your large input, you end up overpaying your smaller ones. To make things trickier, many service platforms tie their CPU to memory. You can get more CPU only if you request more memory. So for CPU-bound functions, users often have to over-provision memory just to get enough CPU. One more thing here is that the resources you request are guaranteed regardless of actual demand. It assumes all resources are needed urgently. So even if your function runs during off-peak seconds, you still pay full price. Such a model is static, as the memory limit is static over time and across invocations. It is also linear for the CPU and memory relationships. And it is interactive only as it assumes all resources are needed by the client urgently, even in a low demand time, and all applications are latency critical and should get their resources at any time. So we call such a model slim billing model is static, linear, and interactive only. In short, you pick a memory limit and your cost is just the execution time multiplied by that limit. But this simplicity comes at a cost. You are often charged a lot of unused resources. So we found that it's not a true pay-for-use for service platforms. But for providers, it guarantees the revenue as all allocated resources are billed, which helps explain why such a platform is very popular today. To tackle this problem, we propose a better billing model, and we explain what kind of system is needed to support it. First, I will introduce our new billing model, nearly pay-for-use. It can benefit both providers and customers, and we'll see that later. Then I'll walk through our system, Leopard, a serverless platform to implement nearly pay-for-use. It introduces both kernel-level innovations and platform-level changes to support the nearly pay-for-use. And finally, I'll close up with some evaluation results on Leopard with the nearly pay-for-use. We can see it will have higher throughput for providers and lower cost for customers. So what should a better serverless billing model look like? First, it should offer the right number of knobs for users to tune. Not too many, but enough to let users express their resource needs flexibly. Second, the billing model itself should aim to closely match true for use. At the same time, we wanted to ensure the provider profitability. We don't want to rob the provider to benefit customer, meaning we shouldn't have any uncharged resource allocations. So our intuition is to break from today's slim style constraints to make it closer to true pay-for-use. We want to decouple CPU and memory, and we want to let users express their urgency for their resource demands and allow them to land unused allocations to others in a best effort manner. To let users express their CPU needs flexibly, nearly pay-for-use introduces two knobs. The first is the CPU cap, the maximum number of CPUs a function can use. The second is spot CPU. It is a subset of the CPU cap that the function doesn't need immediately. Users can say something like, I don't need these CPUs urgently, but I'll take them at a discount price if they are available in your system. The remaining CPUs are reserved CPUs. These are guaranteed to be available when needed, which helps meet the latency requirements. In this example, the machine has 4 CPUs, and function 1 requests all 4 as a CPU cap, but marks only one of them, CPU 3, as a small CPU. So function 1 has full access to CPUs 0, 1, 2, but uses CPU 3 as at a best effort basis. So when function 1 isn't fully utilizing its reserved CPUs, they can temporarily land to another function, say function 2 here, as a small CPUs. But when function 1 needs them back, the system should make a strong requirement that it regain access immediately. And when CPU 3 becomes idle, the CPU gives function 1 an opportunity to use it as a spot core. And similarly, nearly pay-for-use also introduces 2 memory knobs. First, memcap defines the upper bound of the memory usage, just similar like the CPU cap. And second, preemptible mem lets the user specify whether their function's memory can be reclaimed during the execution by the serverless platforms. And setting this knob to true means I don't need all those memory urgently, just like the spot CPU things. Now let's talk about how nearly pay-for-use calculates the CPU cost. The base cost is simple. It's a reserved CPU multiplied by the execution time, billed at a regular rate. And the first idea is that reserved CPUs are more valuable than spot CPUs, and the customer paid for spot CPU as borrowed CPU time from others with a lower rate. And the second key idea is minus the time your function lands out its idle CPUs, which is also earn users a discount. And we apply a similar structure to memory billing as well. So in this user land billing model, users can sell or buy their idle or spot CPUs with each other without affecting the provider's revenue. So that wraps up our first part of our work. It gets us much closer to true pay-for-use as it breaks static, linear, interactive-only constraints. And at the same time, it preserves providers' profitability, since the discounts for borrowed resources are paid by the borrower, so the provider's revenue stays the same. In short, this nearly pay-for-use model strikes a balance between provider and the user side. It gives users flexibility and take a step to true pay-for-use, but without sacrificing the provider's revenue. Now, in the rest of our talk, we turn to the system question. What kind of function as service platform do we need to actually support the nearly pay-for-use? We found it's not a trivial question. We cannot just change the billing function itself. Let's firstly take a brief look at how a typical function as service platform works. So when an invocation arrives, the load balancer routes it to a worker, and the admission controller on each worker decides when to admit it and activates or reuses a sandbox if resources allow. And if the memory is tight, the sandbox reclaims space by removing cache sandboxes. Function as a service platforms use containers or virtual machines like Docker, Firecracker, Kubernetes pods, etc. to isolate CPU and memory across function instances. But they all relying on the Linux C groups for the resource allocation. CPU isolation also depends on the CFS, which allocates CPU time proportionally across task groups and balances tasks across cores. And for memory part, C groups enforce hard caps, and the OM killer is invoked when these limits are exceeded. We implemented our system Leopard on OpenLambda, but this design generalizes to other function as service systems. So nearly people use brings new requirements to this function as service stack. We now need a smarter load balancer and admission controller to handle nonlinear calls-aware functions. And the sandbox evictor must prioritize evicting the preemptible instances under the memory pressure. And on the Linux side, two changes are essential. First, we need a new CPU reservation mechanism that guarantees full access to reserved CPUs while allowing the best effort sharing of the small CPU at the same time. Second, during memory exhaustion, the OOM killer should hand over eviction control to the user space policy, like the sandbox evictor, who know which function is preemptive, which is non-preemptive, who is executing longer than the other one, rather than killing the processes blindly based only on the kernel level information. In this talk, I will only focus on one key challenge as the time constraints and how to implement this efficient CPU reservation. And for other details, feel free to check out our paper. So before showing our solution, let's first understand why Linux falls short on providing such an efficient CPU reservation. Linux C group offers two approaches: CPU pinning, which restricts a task group to a fixed cores, and weighted sharing, where CFS allocates CPU across task groups proportionally based on configured width. And CFS is the Linux fair scheduling. And we run a simple experiment to show that we have two functions, each reserving 16 CPUs on worker, and function 1 runs 32 long-lived threads and is willing to pay actual as the small CPUs. And function 2 starts with a single thread and later fans out to 16. And we first evaluate CPU pinning, which assigns 16 dedicated CPUs to each function so that both of them reserve 16 CPUs. And this plot shows the CPU usage over time. Dark blue means function 1 is running at this time using this CPU, and light blue is function 2. White means the CPU is idle at this time. What we see here is that function 1 and function 2 each get isolated access, but when function 2's CPUs are idle, function 1 can't borrow them, even though it's willing to pay. We then evaluated the weighted sharing, giving both function 1 and function 2 equal CPU shares, effectively reserving 16 cores for each. And in the beginning, this works well. Function 1 can borrow the idle CPU time from the function 2, so the spot CPU mechanism works. But when function 2 fans out, it can't immediately reclaim its 16 cores. Instead, it shares cores with function 1 for hundreds of milliseconds, which is intolerable in serverless environment, causing around 20% of slowdown for the function 2. To overcome this limitation, Leopard introduces a new C group interface called CPU.reserveCPUSet. Let the C group specify CPUs it reserved. To correctly implement this, the Linux CPU scheduler should guarantee highest priority access to those CPUs when needed. Importantly, this reservation should be non-exclusive. The C group can still use other CPUs outside this reserved CPU set to enable the small CPU sharing. And we modified the Linux CFS scheduler in two key ways for these requirements. Instead of relying on fairness for isolation like CFS does, we directly enforce priority for isolation. Second, we introduced the core-specific policies. On the reserved cores, a task top priority and immediate preemption is enabled. And on other cores, the same function can have different flexible policies. The same task behaves like a small task on another CPU. It has a lower priority and best effort basis. We keep the design of CFS to ensure the fairness inside the task group and the fairness to use small cores across different task groups. So this is transparent to Linux functions. And this design ensures that reserved CPUs are always available to the right C group while still enabling sharing when possible, which currently Linux doesn't support. Finally, let's take a look at how it performs in practice. We evaluate on workloads, which is a trace with a series of invocations with varied resource usage behavior. So it is more like today's realistic serverless workloads. And compare 4 billion models. The static linear interactive only model, this is what we saw earlier. This reflects today's popular commercial platform like AWS Lambda, Azure Function, or Azure Function with a premium plan and the Google Cloud platform. and static interactive only model, which is similar to SLIM, but decouples CPU and memory billing. And straight pay-for-use. This is an ideal baseline for customers that charges only for actual resource usage, but it might be harmful for the provider as it gives some resources for free, give the unused resources for free, even if it's allocated to the user. And finally, it's our proposed model. The first question we ask is, how does Leopard with nearly pay-for-use perform from the provider's perspective? And to answer that, we measure system throughput under different billing models. So moving from SLIM to SIM gives a 1.3 times improvement, simply by decoupling the CPU and the memory billing and allowing better resource matching. But when we switch from SIM to nearly pay-for-use, throughput improves by an additional 1.6 times. This is because nearly pay-for-use enables fine-grained sharing when functions' idle allocated resources cannot be used to satisfy another's non-urgent need, and leading to a much better overall utilization than the provider throughput. Next, we ask, can Leopard with nearly pay-for-use reduce customers' cost? Customer cost and provider revenue are naturally linked, so to make a fair comparison, we normalize the billing models to achieve the same provider revenue per machine per time unit. Then we can only focus on customer cost per invocation. This is a fair comparison between the billing models. And this graph shows the CDF of invocation costs relative to SLIM. The x-axis here shows the cost ratio to SLIM. Values to the left of 1 means that the invocation is cheaper than it would be under the SLIM. And the y-axis is the percent of the invocations. So under SIM, around 50% of the invocations are cheaper. It helps, but it is not consistently. Surprisingly, straight pay-for-use can actually cost more than SLIM for many invocations. And in contrast, nearly pay-for-use reduces the cost of nearly every invocation. This is because it increases the cluster utilization through resource sharing, letting users treat non-urgent demand and user allocations. And we also see that batch tasks save more. So in a conclusion, we started by observing that today's serverless billing models aren't truly pay-for-use. To address this, we designed a new billing model nearly pay-for-use. It approximates ideal pay-for-use much closer for the customers, and it still preserves profitability for providers. And to support it, we built a system Lambda that implements this nearly pay-for-use. This requires both kernel-level changes and platform-level changes. And our work demonstrates that billing models should be considered not as an afterthought, but as a central part of the system design. Thanks for the listening, and I'm happy to take in any questions.